Our topic for today is potential energy due to a dipole. This we have already done. Potential energy due to a dipole we have done. This is dipole in an external field. In an external field. So things get interesting here. So one, we will have an external field, and one, we will also have a dipole, and we have to find out what is the potential energy of that system. So first, let us make that external electric field which is uniform. So this is an external electric field. Okay. So this is your external electric field, and we will create a dipole out here. Now I'm drawing it deliberately slanted, and I'll tell you why I have drawn it slanted. Okay. So let's say this is minus Q, this is plus Q. Obviously, our distances are A and A, right? A and A. And the dipole moment, the electric dipole moment, always points along the direction. So the electric dipole moment is in this direction. Right? This is the electric dipole moment P. Okay. Potential energy due to a dipole in an external field. Now let's recall, right? The first thing is we have a dipole. Try to recall. A dipole will have a plus Q and will have a minus Q. Distance of separation between them is 2a. Dipole is specified by the dipole moment, and the dipole moment always points from minus Q to plus Q, means in this case the dipole moment will be in this direction. This is given by Q multiplied by 2a. All these are known to us. When you place a dipole in an electric field, then the net force is always equal to 0. These are things which we have discussed. The net force is always equal to 0, but there comes something which is known as a couple. The net force will be 0. The net force here is also 0. The net force here is also 0, but there is a couple. What is this couple? The couple is due to this much of the arm. Okay, say this is the arm. This one. And if you see the net force, this is the force and this is the distance. This is the force and this is the distance. And how much was this distance? If you take this as A and if you take this as theta, then this becomes A sine theta. Correct? This also becomes A sine theta, and this becomes A cos theta. This is A cos theta. Clear? What is sine of theta? Opposite side by hypotenuse. So this becomes A sine theta. So what is a couple? A couple is force multiplied 2A, force multiplied by twice of this. So if you see this couple is 2 times whatever is it, A sine theta multiplied by what? Q into E. QE is the force. QE this side, QE that side. And this is nothing but what was your torque? 2AQ, 2A and Q, and then you have E into sine theta. So this was nothing but the torque, which is 2aq torque into E. This couple actually gave you a torque, and the torque, sorry. So this is 2aq into E to sine theta, which is PE sine theta. And this was nothing but the magnitude of the torque. So the torque experienced by a dipole is always P cross E. This much we have learned already in what you call chapter number 1. Okay, torque experiences. Now, what does this torque do? What does this torque do? Let's try to understand. Now you have an external electric field, and the external electric field is E. So whenever your dipole is aligned along with the electric field, means the dipole moment is aligned along with the electric field, at that time what happens? It is in a state of equilibrium. But that alignment can be in two types. One is that it is aligned with an angle 0 degree, means P is on this side, E is on this side, then it is happy, it's a stable equilibrium. But if you have the P on that side, then it is an unstable equilibrium. Should you disturb it slightly, it again brings it back. So our analogy should be, why is this torque important? The torque is important because if I displace my, I said now I will be drawing it with an angle theta. That means if I displace my dipole a little bit in this manner, the torque brings it back to its shape. This is this torque. So what does this torque do? The torque restores the dipole again in such a manner, that the dipole moment aligns itself with the electric field vector. Is this clear? Now what we will do, we will say an external torque tau external, displaces the dipole from theta 0, some reference, to a point theta. Now you have brought the dipole is in this manner, stable equilibrium. You are applying an external torque. We are applying an external torque, and we have displaced this dipole. What will happen? As soon as you apply the external torque, this torque will also come into picture and will try to restore it back. So don't you think that the amount of torque you have to apply to bring it from theta 0, say this is theta 0, to theta, has to be equal to this torque? There is a, how much energy, how much force do you need to pull a spring? As much as is the spring force, because the spring force will try to bring it back. You have to apply the same. So we are applying an external torque tau ext that displaces it from theta 0 to theta. Don't worry about where is theta 0 and all. Theta 0 is reference. So from the reference, we have displaced it to where beta? We have displaced it to some theta. That means this tau external must be equal to the torque which is given by PE sine theta. It has to be equal to that. Agreed? Now, the work done. Acha, why am I saying work done? If you apply an external torque and you take the dipole to this position, don't you think the dipole has been energized now? Yes, so the dipole will come back here. So you are doing some external work. Now we're trying to calculate that work done. Just see, you're applying a torque to move it to this position. You're twisting it to this position. You have energized it. You have added more energy to it. So we're trying to calculate that work done. Understood? Now, work done, when you compare it with force, it is always force into displacement. So we write in terms of force, work is R into F. But when you do in terms of torque, it is tau into theta. That is rotational motion, grade 11. Work in terms of torque is always torque into the theta. Theta is the angular displacement. This is the angular component, angular displacement. Linear component, linear displacement. So we say the small work dW that we are going to do is given by the torque multiplied by the d theta. The small angle that we will do. Small work is equal to the torque multiplied by d theta. What is the torque? The torque is PE sine theta d theta. Is this understood? Now, if you want to calculate what is the work done, why are we calculating work done? We want to find out potential energy. Whatever work we will do will be stored as potential energy. Okay? If it is confusing you, once again, what is a dipole? A dipole is an arrangement. These all are clear. A dipole is an arrangement of a minus q and a plus q separated by a finite distance of 2a. This dipole is being placed in an external electric field. Whenever you place a dipole in an external electric field, there will be two forces which will be seen. What are the two forces, sir? We have forgotten. Don't forget. One force will be seen on this side, and one force will be seen on this side. Yes or no? This force value is equal to QE. This force value is also equal to QE. Okay, direction wise minus QE, QE. These two forces are creating a net force of 0, but do create a couple. A couple is when two forces are separated by the same distance. What is the value of a couple? Is given by 2 times the force multiplied by the difference of separation. So what is the force? The force is QE, 2 times the force multiplied by the separation. The separation is A sine theta. Force 2 times separation. This is nothing but the torque that you studied. The torque is given by PE sine theta or P cross E. Clear? Torque is a vector quantity. What does this torque do? The torque always aligns the dipole along the direction of the electric field. Means aligns the dipole moment. While aligning it, it can align in 2 ways. One is P is along E, theta equal to 0, stable equilibrium, or P is opposite to E. In that case, unstable equilibrium, but still it will be aligned. But should you just displace it, it will not come back to the same shape. One complete turn it will make. Same thing we are doing. Now we want to find out what is the potential energy of this configuration. So in order to find the potential energy, we say that there is always a torque which does what? Which brings it back here. But I am introducing an additional torque because the potential energy, now comes the question, how do you measure the potential energy? Beta, potential energy is a very referential thing which is different at different places. Potential energy of the pen here is different. Potential energy of the pen here is different. H1, H2, MgH1, MgH2. Got it? So the reference is the ground. So whenever you are measuring the potential energy of a twisting thing, you have to have a reference angle. You have to have an angle by which you have rotated it. Yes or no? It's a circular spring. So you have this much less potential energy, this much more potential energy. So there has to be a reference. So we say, how will I measure the potential energy? Sir, there is no such device. Do one thing. You do some work on it and measure your work. Your work will get stored as the potential energy. As I sweat to pull the bow has that much potential energy equivalent to the sweat that I have spent. So what I do, since this is a rotational thing, I can give a force. So I give another external torque. What torque did you give, sir? Sir, I rotated it from some theta 0 reference to theta. Theta 0 to theta. Theta 0 to theta. While I am rotating it, the internal torque again says, get back to the shape. So I have to rotate it with a torque which is equal to the internal torque. So I say that, say an external torque tau txt displaces the dipole from theta naught to theta. In that case, the external torque has to be equal to that torque which is already inbuilt in that system, which is P sine theta. Now I want to measure potential energy, so I have to measure how much sweat I am going to put on it. That sweat is nothing but the work done. But since the theta is variable, whenever the displacement is variable, what do? Work is said to be F dot ds. Similarly, here it will be tau dot d theta. But you should know this, that the work in rotational motion is tau theta, linear motion is r into f. This is rotational motion. So tau into d theta. Have you understood so far? Now clear. Now if you want to see the network is an integration of all the small works. From where to where did you rotate? You rotated from theta 0 to theta 1. Oh, sorry, theta 0 to theta. You rotated it from here. Agreed? That means you have to integrate PE sine theta d theta from theta 0 to theta. This is what we have to do. Is this much clear now? Getting in line a little bit? Come. So we said that the work done is equal to the integral of theta 0 to theta theta 0 to theta d work, which is theta 0 to theta tau d theta, which is theta 0 to theta pe sine theta d theta. Any confusion, children? Now no confusion. Okay, let's see now a little bit of integral calculus. ddx of cos x is sin x. This is the differentiation. So when you, this is called derivative. If this is the derivative of this, so the antiderivative should give you the function back. That means if I integrate sin x dx, I should get back what? I should get back minus cos x. See, ddx of cos x is minus sin x. So sin x integration is not possible. So you will be integrating basically minus sin x. Minus sin x will give you cos x. So sin x integration is minus cos x. Is this understood? So our work done now becomes equals to negative pe cos theta. Okay, we have integrated it, negative pe cos theta. These are called definite integrals, children. That is an indefinite integral. So here we will always add one constant of integration, which you learn. But this is a definite integral. Here we do not add constant, we just add the limits. Our limits are what? Theta 0 to theta, right? How this is calculated? Very easy. You will be taking, this is known as the upper limit, this is known as the lower limit. So whatever function you see, function at the upper limit value minus function at the lower limit value. What is the function now? Cos theta is the function. So our next step will be to get a particular value. So negative p I am retaining as negative pe. Now look, this is cos theta. Cos theta is to be evaluated for its two children, theta naught and theta. So it is always cos elder child minus cos younger child. Elder child is upper limit. So I will write here cos of theta, upper limit is theta itself, cos of theta naught. Is this clear? And if I want to get rid of this negative, I can now write pe cos theta naught minus cos theta. I just took the negative common. Is this thing understood? This is known as the work done. So this is work done, means this should be the energy also of the system. Now this is, how are you saying? You are trying to say, now so this is like this, see, this is ground level. Let me give you an example. This is man standing here, this is man standing here, right? And I'm asking you and say this is the center of the earth. This is H0, this is H. I ask you, what is the energy of this man here, potential energy? You will say, sir, we can't calculate potential energy. We can only calculate potential energy difference. So what is the difference of potential energy? Here it is mgh1, sorry, mgh, and here the potential energy is mgh0. Where are you measuring it? From some absolute, that is the center of the earth. Same definition you have got here. But now you say, no, give me a particular value. So you have to bring a reference. What is the reference? You said, okay, let's create the reference here and let's assign this reference as 0. The height is 0. Then what is the potential energy? mgh. So we have to give a reference here also. In NCERT, the reference of theta naught is given as pi by 2. Why do you give pi by 2? Pi by 2 is 90. Cos 0 is 1, cos 90 is 0. So if this is the reference, this is called the reference. Reference. So reference means it is something like this. See, that means originally dipole is here. Look, dipole is not here. Dipole is here now. You're moving from here. This is the reference is from 90 degree. Okay. Why from 90? It will become very interesting. Just see. The reference is given pi by 2, right? Then cos of pi by 2 becomes equals to 0. My W, which is nothing but the potential energy of the system, is given by minus PE cos theta. Minus PE cos theta. Did you understand? Minus PE cos theta. Okay. From here, some important interesting things. What is theta? Theta is equal to angle between P and E. P and E. If you want to have a little bit of the diagram, the E is in this direction, and let's say my dipole is like this. This is theta, and say this is P. Okay, this is P. What is the potential? Achha, tell me. A system wants to be always in higher energy state or in lower energy state? Where is it more stable? More. Okay, let's give you an example. There's a child in the house who just goes on creating nuisance in the house, running around, jumping around, all around. The parents are most happy when the child goes to sleep. At that time, the child is most stable. He or she has expelled all his or her energy, right? The more energy a system is, the more disbalanced the system is, the more entropy the system has. Just try and see one more example. I ask you to sit on the bus, you are very comfortable. The moment I ask you to stand, your body CG has moved up. You start holding, you are not that comfortable. I ask you to stand on the roof of the bus and I ask the bus driver to drive the bus. You will be thankful if I allow you to sit on the carrier of the bus, on the roof, and you'll hold. So the more lower you come, it's more stable. That's why double-decker buses are not that stable. And a double-decker bus, nobody will ask you to sit on top if there is nobody at the bottom, because the CG has moved up. The system always comes to lower energy. Our dipole was more stable when it had a 0-degree angle. System's energy was the lowest. Let us check now. Okay. So what is the energy of a dipole? The energy of a dipole is minus PE cos theta. Okay. You can also say the energy of a dipole is minus of P vector dot E vector. The dot product is always PE cos theta. Right? If theta is equal to 0, U is equal to negative PE, some value. Then cos 0 is equal to 1. So U will be equal to negative PE. Agreed? This is actually lowest energy. We will find out lowest energy. Got it? Okay. Then if theta is equal to, say, 180 degree. If theta is equal to 180 degree, that is theta is equal to pi, then cos of pi is equal to minus 1. Your U becomes PE, maximum energy. You imagine, do you remember, if you bring the dipole to this side and make it 180, the dipole has the maximum energy now. It will just go and flung back and do it in this manner. Right? And if theta is equal to 90 degree, that is theta is equal to pi by 2, then the potential energy is equal to 0. And this is known as the reference level. Sir, how did you get this? You only took this. You only took this reference level. This implication is very interesting. This part is, I hope you have understood this part. The value of U is given as negative PE cos theta. So we are seeing three different orientations. What are the orientations? If the dipole, let's say this is the dipole moment, my pointer is in the dipole. If it is along the direction of E, angle is 0. Then what is the value of potential energy? PE cos 0 minus PE cos 0. So cos 0 is 1. So it is minus PE. This is the minimum energy. It's a negative energy, means minimum. It's most happy to stay here. If you make it 90 degree, then it becomes 0. Cos 90 is 0. Why 0? You only took as 90 degree. This is your reference. From reference, if you make it 0, then it becomes what? If you make it, if you make it from here, if you make it from 0, it is more stable. At 90, it is 0. But if you actually turn it 180 degree, then the value of the potential energy is positive PE, which is the maximum energy. Because if you do this, system will come back this side. Have you understood? Now, this derivation in NCERT is also derived using potential due to two charges also. So what did we, you might get a little bit confused when you look at the book, but to make things simple, we are doing this thing. Look, we are trying to find out electric, this will take some time, okay, potential energy due to a dipole in an external electric field. This is what we were trying to do. We first derived it using the concept of the torque, which is tau equal to PE sine theta. That is what we just did. And we said that the electric potential is given by U, which is equal to minus PE cos theta, which is also equal to minus of P dot E. Based on this, we got three configuration. Number one, theta equal to 0 degree, the U is minimum, which is equal to negative PE. Sorry, theta equal to, yeah. Number two, theta equal to 90 degree, U is equal to 0. This was the reference. And third, we got theta equal to 180 degree, U is equal to PE, which is the maximum one. This was when you are deriving it using torque. Have you understood? Now, our next derivation means trying to understand the same analogy using our previous class. In previous class, what did we study? In previous class, we studied what is the electric potential energy of a system of two charges placed in an external electric field. That's same. A dipole can be called as two charges. So our next, the same thing we will try to see with the analogy of, we will try to see it as electric potential energy of a system of two charges placed in an external electric field. Children, why are we doing this? The system of two charges is analogous to the dipole. So here basically both the things are same. Approach will be different, but we will arrive at the same thing. Approach will be different, but we will arrive at the same thing. Okay? So let us try to understand this now. So our system is something like this now. What is our system? Our system is, yeah. So I have two charges now. I have a charge minus Q. I have a charge plus Q. Okay. The two charges are also separated. So these are my electric fields, and I will also have okay, these are the electric fields. Now try to understand one thing. What is this distance this distance is a, this distance is a, this is the electric field, and obviously here I also have my dipole moment. This angle is theta, this angle is theta. How much is this total distance? 2a, 2a. But if you see, what is the displacement between the two charges along the electric field? Why I need that value? Because you always remember, we have this formula which says that the electric field is always equal to V upon L. Sometimes so it is the electric field, the potential difference delta V is always given as the negative of the electric field into the length between them. This length is the displacement. This length is the displacement. Now try to find out what is the displacement between the two charges along the electric field's direction. Displacement means shortest distance between the two. Shortest distance between the two. The shortest distance will be this distance plus this distance. Displacement. Are you getting it? Draw two vertical lines out here. So if you think that it is still complicated, you want to find out displacement, the displacement can be found out like this. I'm worried on this. This is something that I want. This is the displacement between the charges along the electric field. This is the displacement between the charges along the electric field. So what is its measurement is equal to what? Its measurement is equal to this measurement plus this measurement. Do you agree? And this measurement is how much, beta? A cos theta. This is A cos theta. So the displacement is how much? 2A cos theta. Is this much clear? Make this much. Okay. Now we have to find out what is the potential energy of this system, right? So, and furthermore, if you want to complicate and make it beautiful, make some coordinate axis also, so that this is some coordinate axis where actually this shows, say, R1, and this is R2. This is the configuration of the system. Okay, this is vector R1, this is R2. All right. So we have two charges, minus Q, and we have a charge which is plus Q. Let us find out what is the energy due to this minus Q charge. The energy due to minus Q charge is given by Q into the potential due to R1, minus Q into the potential due to R1. Is this clear? Okay. Then let us find out what is the potential, say here. U plus means this is due to minus Q, this is due to plus Q. This is Q into the potential at R2. Q into the potential at R2. Agreed? What is the net potential due to the two charges? The net potential due to the two charges is Q due to R2 minus Q due to R1. VR2 minus VR1. Okay. And this can be now written as U is equal to Q times of VR1. Okay, R1 is negative, right? Okay, so my R2 is here. R2 minus, this can be written as VR2 minus V R1, right? So let's calculate what is VR2 minus VR1. The difference of potential at 2 points. VR2 means potential. 1 minute, huh, children? Yeah. VR2 means potential here. VR1 means potential here. What is the potential difference between 2 points? The potential difference between 2 points is always negative of the electric field into the displacement between them. That comes from that formula, that E is equal to minus V by L. Negative of the electric field into the displacement between them. So what is negative of the electric field? Negative E. And what is the displacement between them? Sir, the displacement between them is 2A cos theta. So this is equal to, right? So fine, this is equal to this. So can you find out what is Q? U equal to, U is Q times V at R2 minus V at R1. That means this expression multiplied by Q, QE 2A cos theta. This becomes what equal to 2AQ, which is minus PE cos theta. Okay, have you brought the expression same as this one, minus P cos theta? But there is a small caveat to this also. Hang on. Potential due to two charges, the potential of this configuration is due to three things. Potential due to this, potential due to this, and the potential between the two. Just remember the first problem that we started today. QVR1, QVR2, and we subtracted a negative 0.7. The negative 0.7 was the potential between these two. So with this, if I am allowed to go to the next screen, we just found that U is equal to minus PE cos theta. This is what we found out. But if you try to find out the net potential, then the net potential should be minus PE cos theta, which we have already found out. With that, you should also add the potential due to the two charges. What is the potential due to the two charges? Minus Q plus Q, agreed? Divided by 4 pi epsilon naught. And what is the difference between the two charges? QA. Got it? However, children, when we went by the torque analogy, we found that the potential energy, was just minus PE cos theta, which we wrote as minus P dot E. Here we are getting one more additional term. This additional term is neglected. Why is it neglected? It is neglected because this is a constant, this is a constant, this all are constant, this is all a constant. So you can basically say this expression tells you it is PE cos theta plus some constant, say alpha. Wait, don't write. Get the beauty of it. Plus some constant alpha. When you actually measure potential, tell me, do you actually measure potential or potential difference? You always measure potential difference. This alpha, if it is added in one configuration, it is there in the other configuration also. So the alphas and alphas all cancel each other. Therefore, the unit is taken same as this, and we say U is equal to minus PE cos theta. This part is neglected. Why this is neglected? Because if this is inbuilt, it's like, how much pocket money is there with you today? You say, sir, I have got 50 rupees. How much is with her? She has got 70 rupees. I give both of you 10 rupees each. What was the pocket money difference between both of you before I gave 10 rupees? You'll say, sir, 20 rupees was the difference. I had 50, she had 70. I gave both of you 10 rupees. Alpha, alpha. Now what is the difference of money between you two? Still 20 rupees. So if the alpha is inbuilt in one measurement, the alpha will be inbuilt in the other measurement also. So this, and since the alpha has no role of theta embedded in it, therefore we say that this term can be cancelled. And that's why we come that the potential energy between the, so remember one thing, whenever you are calculating it as a dipole, it makes more sense for you to use this formula, go by the torque approach. If it was not a dipole, any two charges, then by this approach. At the end of the day, it is the potential energy is, torque is always given by P cross E, potential energy is given by negative of P dot E. And if the angle makes 0 degree, then it is minimum. At 90, it is reference. At 180, it is maximum. Is this thing understood? Right. And we always calculate it by giving an external torque. External torque should be equal to internal torque, and then integrate it and find the expression. Based on that, we have one small problem. I think after that, all these potential part ends in your what do you call a chapter, and we will move into conductors, dielectrics, and polarization and capacitance. So let's see one problem. It says a molecule of a substance. So just given you have a molecule. This is a molecule of some substance, we don't know. A molecule has a permanent dipole moment. That means the dipole moment of this is given as, and I'll not use the vector sign because this is just the scalar measurement. The dipole moment is 10 to the power minus 29 coulomb meter. This is the dipole moment of the molecule. Then what do we do? A molecule of a substance. A substance. Children, is this understood? This is a molecule of a substance which has a dipole moment of this much. Then from this substance, we picked up 1 mole. 1 mole. 1 mole means how much did you pick up, beta? 6.022 into 10 to the power 23 molecules you picked up. That's 1 mole. So many molecules you have taken, and you applied some strong electrostatic field and you polarized them. So you basically subjected them to an electric field. Electric field, the value of which is given as 10 to the power 6 volt meter minus 1. See, it is exactly E is equal to V by L. Did you understand? This is a substance whose dipole moment is this much. You took 1 mole and you subjected them to this much of electric field. Basically, this is called polarizing. You polarize them. Initial field is suddenly changed by an angle of 60 degree. Initial field is changed by 60 degrees. So you have changed the electric field by 60 degree. You have to estimate what we have to estimate: heat lost or heat released, heat dissipated, heat released if 100% polarization took place. Let's first understand the words. Okay. Remember, children, what is polarization? We use this word a lot in civics. We say this vote bank is polarized. How did you polarize this vote bank? By the name of caste, creed, religion, whatever. You gave some pep talk and you converted all these voters to your pep talk, and you have polarized them. Means all of them will now vote to the same party. So these were some innocent molecules. Each of these innocent molecules have a dipole moment of how much? Blah, blah. 1 mole of these molecules were taken. These were the crowd. And then you delivered some polarization lectures of what, how much, this much, and 100% polarization took place. Means all of them, if you subject them in an electric field, what happens? They will develop a potential energy, and that potential energy is only basically the heat that they will be releasing. So if they are asking us find the heat, it is a form of energy. We have to correlate this problem to our problem. Our problem is this configuration. You have polarized means you have moved everyone, and this problem, all these should develop some sort of a potential energy. So in nutshell, we have to calculate what is the potential energy of this configuration. That same potential energy will be released by them in the form of heat. Ready? So shall we start calculating now? So how much we have? Dipole moment is there. So what is the net dipole moment. The net dipole moment is 6.0. Okay, the book has not taken 6.022. They have taken just 6 into 10 to the power 23. Simplified it. Multiplied by how much? 10 to the power 29. So how much does it become? 10 to the power minus 29. So this becomes 6 into 10 to the power minus 6 coulomb meter. This is the net dipole moment. Okay. So initial PE, see, don't calculate the PE. You have to calculate, see, it's like this. The dipole will always be aligned. The dipole will always be aligned along the direction of E. At this configuration also they have a potential energy, but that potential energy is the minimum potential energy. Do you get it? You took this dipole and you now twisted it. You now twisted it by an angle of how much? 60 degree. So this is, at this you have initial PE, this is final PE. The difference between the two is the net gain of PE which you will release at heat. So calculate what is the initial potential energy. The initial potential energy is minus PE cos 0. Clear, Zoe madam? Minus PE cross 0. What is the final potential energy? The final potential energy is minus PE cos 60. Right? So what is the delta potential energy? It is always final minus initial. So minus PE cos 60 minus of PE cos 0. So this will become plus. So it's basically PE cos 0 minus PE cos 60. So this is PE minus half PE. Hey, are you writing values or what? Cos 60 is half. Sin 30 is half, so cos 60 is also half. So it is PE minus half PE. So it is half PE, which is equal to half into how much? P, we got the value 6 into 10 to the power minus 6 into E. How much is our E? 10 to the power 6. CBSE will always give you a nice. Yeah. So this is 3. So PE is equal to 6 joules. Right? How do you get 3 joules? I got 6 joules. Something wrong? Hey, what wrong did I do? P minus P is half. Somewhere there is a 6. Some 6 is missing. Net P. P is 6. E. Oh, why am I calculating? Oh man, you people also say I'm doing half twice. Sheh. Three joule. 3 joules is the change in energy, and this change in energy will be dissipated as heat. Did you understand this numerical or not? So you might not get straight. You have to first understand how to map the numerical. The numerical is telling me that there is a polarization that has happened due to which there will be a change in. Always calculate the change. Many people, what is the mistake they will do? They will just straight away put the value of the potential energy. Rather, to make it mathematically correct, I think I should write this like this. This is U. So we should write it as like this, so that you don't make this mathematical mistake. We write U at a point theta is equal to negative of P. U at a point theta. U at a point theta is negative of this. Always write it as u at theta is minus Pe cos theta. Therefore, in this problem, what did you do? You first calculated what is initial potential energy. So here, what did you calculate? U at 0. Final potential energy, U at 60. And then you calculated delta U, which is U at final, that is 60 minus U at 0. This is what you did. Don't just calculate this. This is potential energy at that point. This is change, always change. Okay? So this closes all things with relation to potential energy. There's no more potential energy which will eat you. So you basically studied electric potential difference, potential energy difference, electric potential energy at a point, electric potential between 2 points, electric potential at a point, potential due to a dipole, potential due to a system of charges. After that, you studied potential energy due to a system of charges, potential energy due to a dipole, and now you're fine to go to capacitors slowly. We'll learn a little bit about conductors. Maybe 2 more classes we will need before we push on to